Okay. Now I will make you good. Yes, sir. Now you can start, sir.
Yes, 1 minute. Yes, I will take my tab.
Yeah, sure.
Is my screen visible?
Yes, sir. Your screen is visible now.
Okay. First of all, I thank you, SVRI College of Engineering, for providing me this opportunity in delivering this session. So the session topic is thermal management of buildings and processes. So basically, before getting into the talk, I just want to tell about our institute. Yeah, one slide about a brief introduction about our institute. So actually, our institute name is Rajiv Gandhi Institute of Petroleum Technology. So we have our main campus in Amethi in Uttar Pradesh. So where we have BTech, MTech, and PhD programs admitted through JEE Advanced and GATE. Similarly, we have our Bengaluru campus. It is a research institute. We have only MTech and PhD programs. So these are the 4 MTech programs: renewable energy, electric vehicle technology, data science, and artificial intelligence we have in MTech programs. And also we have PhD openings in our vacancies in our institute. Okay, so to start with, this is a brief outline of my session today, as it is a more of a hands-on thing. So for the first 1 hour, I'll be delivering a talk, and the next 1 hour I'll be doing hands-on. So first of all, to start with motivation. So why thermal management is important, and followed by, there are 2 topics. So primarily focused on thermal management of buildings using certain ways, and we can also have a short look on thermal management of processes. So why thermal management? So from the slide, you can see that a laptop on the left side, you can see that there is a laptop, and there is an uneven temperature distribution you can able to see. That means in certain areas, like where the processor is there, the heat generation is more. And in other areas, the heat generation is less, the temperature is less due to that. So if it is not managed properly, the life of the laptop will be reduced because of the continuous high temperature will give a stress on the processor. Because of that, even the performance of the laptop is also reduced. In the right hand side, you can see that the thermal runaway propagation in batteries. So batteries is a very key area nowadays, getting much attention. So, but it has its issues like thermal runaway. Like if any one of the cell got failed and it caught fire, that can be propagated to all the cells, and the entire scenario can lead to an explosion. So these are all crucial areas we have to address. So there comes the thermal management. So what is thermal management? It is nothing but controlling temperature through technology. So we have to control to an optimum temperature or a safer temperature by use of technology. Normally, predominantly, we use the concepts of heat transfer, such as conduction, convection, radiation, and certain related processes to control the temperature. Okay, so especially it is not only performance, even the safety is also very important. So thermal management is a very broad area. Now it's get much attention in the industry side. So it has various applications. Like people who work in one area, they can even easily switch over to other domains because ultimately the core problem is one and the same. We have to manage the heat. We have to manage control the temperature. So if a person equipped in one area, he can easily have a he can easily improve in other areas also. You can see from the slide I have just listed out some 5 areas. Even many areas are there for thermal management. So you can see the buildings occupy, say buildings consume about 40% of our primary energy. A huge amount of energy is being consumed. Like for example, in the colder regions, so you need a requirement of heat for a comfortable stay. So in the same opposite side, in the hotter regions, you need coal to have a comfortable stay. So huge amount of energy is spent on heating or cooling of buildings. So here actually, if we are able to manage the temperature wisely, so thereby we can able to cut down our energy cost. And of course, batteries I have told, and electronics. You can see the second peak downward. So you can see that the temperature in certain areas, you see, for example, this areas or even 116 degrees Celsius. So, but the threshold temperature in most of the electronics is about 95 degree. That is the maximum temperature that can be reached. And the safer operating temperature is 75 degree in many of the latest equipments. So we can able to see that there is a huge temperature disuniformity, and we have to avoid these situations for safety as well as performance. And even you can see in this figure that some of the components got fused or melted because of the extreme temperature. So this we have to manage. So basically, we use these are the laws behind the fundamental laws of fundamental laws as well as the heat transfer rate laws. These laws help us in identify how much amount of heat extraction can be done for a specified application. And these are the fundamental laws which drives the flow or energy. And these are the laws which can be used to find out how much heat we can able to dissipate. So before getting into the thermal management of buildings, I just want to chip in about the steps in numerical modeling and simulation. Of course, this is the fourth day. You all might be well aware of the steps in numerical modeling. It's just a recap. So one, to start with, I just want to explain the difference between what is modeling and what is simulation. So many people still have a confusion about the terms modeling and simulation. They take both are same, one and the same, but in actuality it's not. So modeling is nothing but it is the act of building a model. So which means you have a problem in front of you, you have certain inputs in front of you, and you are able to develop a model with the given inputs. So assume you have a building and you have some boundary conditions are there, you have some temperature given, you have the properties of the building. So you are just creating that building in the software like such as COMSOL. So that is what is called modeling. And the second one, simulation, is nothing but use the model for a simulation, which means run the simulation to extract the outputs to get the answers. Okay, that is what is called simulating. So we all know that in the software COMSOL multiphysics, we just start with creating a geometry. Whatever the dimensions, accordingly, we will create a geometry, followed by we just assign the materials. So in some cases, it is not required where you have predefined properties for the problem. It is not required, but it is easy or it is recommended to use the material library available in COMSOL to assign the appropriate materials. And followed by that, incorporate the governing equation. This incorporating is nothing but choose the correct physics. In COMSOL, you have many physics available. So for our given problem, which physics will be more appropriate? We should not choose the wrong physics. So once the physics is chosen, automatically the governing equations are incorporated. Then after that, to solve the problem, we have to specify the boundary and initial conditions. So if the problem is a stationary problem, so I hope you all aware of what is a stationary problem and a time-dependent problem. So in the case of a stationary problem, so boundary conditions is sufficient. Because there is no time dependency, the initial conditions are not needed. Okay, so but in the case of a time-dependent problem, so we need both boundary as well as initial conditions. So once we given these corresponding boundary and initial conditions, so we can move to discretize the problem. So one more point I want to address here. So incorporate the governing equations is normally PDE. It is partial differential equations. Or in rare cases or in simplest cases, it is ODE, ordinary differential equations. So the PDE plus boundary conditions is equal to what is called boundary value problem. Okay, and in some cases where PDE plus initial conditions, those are generally called as initial value problems. Fine. So in heat transfer, most of the time we face boundary value problems. Then the next step is discretize the geometry. That is nothing but meshing. So that we can discretize into several elements. It is a COMSOL multiphysics is a finite element method tool. So, and our equations can be applied on each and every element over several iterations to arrive the solution. So after meshing, we can solve the model. So for solving the model, we have options of choosing multiple solvers available to us. So some solvers take more time, but the accuracy, the strategy, the convergence is good. In some solvers, it may solve fast, but the accuracy may not be good. Fine. So after solving, we can able to extract the results. That is what is generally called post-processing. So post-processing is a very important one because, see, even if a complex problem is solved, but if we are not able to show our results, that it will not get attention. So post-processing is a very important step. So this is about our just motivation behind our session and thermal management of buildings. So I have told there are three things I will be covering in thermal management of buildings. One is using solar energy, because solar energy is a renewable energy available in free and plenty, and we can utilize it to the maximum. The governments are also recommending that. So how we can utilize solar heat in buildings? So the picture, what it is shown is a solar house. Okay, so before that, we are all aware of the fact that the sun rises in the east and sets in the west. That is known to all. But see, in the summer and winter, across the seasons, the sun will take a different path. So the sun will take a path which is closer to zenith in the summer. That is why we have a lengthier day, and in the winter, it will rise far from the zenith. So it will take less day. And so how can we use that in buildings now? Okay, this also can be simulated in COMSOL. So by giving the radiative boundary conditions and the convective boundary conditions for a particular room. So we can see that summer we don't want the heat, so we can keep this solar water heater or whatever the components. And winter we want to utilize the heat, so winter sun is somewhere like this. So it is somewhere here. So we can make use of the windows to take the heat. Okay, and moreover, we can able to store the heat using the solar water heater, and we can able to supply the heat to the panels. So by this way, we can able to manage the heat in the solar house. There are many benefits. It is free of charge, reduce carbon dioxide emissions, it cut cost, operating expenses are low, and it is a comfortable stay can be achieved. So there are broadly two types of heating. One is active and another is passive. So active utilizes the pumping, that blower or either blower or a pump. Okay, we have solar collectors, we have storage units to store the heat, so that in the night we can able to utilize the heat for later period. Okay, so normally, but solar alone units are not recommended because we can have a smaller size conventional system like a gas unit or something like that to have to afford reliability, because we can be fully reliable if we have a auxiliary system attached to the solar system. So let me explain a very standard solar hot air system. So ultimate aim is we have to heat the air. So in cold, in winter time, so okay, the heating cost is predominant. So how to cut that? We can use the solar. So the cold air from the room is sent to the collector. And this picture is taken from Duffy Beckman. This is a famous book on solar engineering of thermal processes. Okay, so the air is getting heated in the collector. Of course, one more point I can say here: the collectors can also be modeled in COMSOL multiphysics. So even the evacuated tube collectors is possible to model in COMSOL multiphysics. So, and once the hot air is coming out from the collector, it is very, very hot. So we can utilize that energy to heat the water. There is a preheater tank. And then we can able to send to our room so that we are getting a warm air. So we can able to achieve thermal management in the buildings. So initially we have taken the excess heat from the hot air that can be used to supply domestic hot water systems. So we can able to achieve, we can able to get some hot water for our domestic purposes. And the pebble bed is nothing but a storage system. If at all there is no requirement of warm air during the day, then it can be stored in the pebble bed storage system, and that can be used in the night time. Similarly, there are many advantages here. There is no freezing problem, no boiling problem, no corrosion problem. High degree of stratification is possible, which means that as the specific heat of air is low and density is also low, we can able to achieve a high degree of, means the starting region will have a high temperature and the end region will have a low temperature. The difference in temperature across layers is huge. That is possible. So control equipments are available. So, but on the other side, we have pumping cost is high because we all know that air, the specific volume is high. So because of that, the pumping cost is high. And large volume of storage is required because the specific heat, the storage here means the pebble bed storage, of course, and if any extra additional air storage. And leakage is a problem and lower capacity. So to address these issues, we have the hot water system, solar hot water system. Here we have, so I can say from anyhow, in both hot water as well as hot air system, we are heating using air only. Our end fluid is air only, but the working fluid in this circuit is water. In this area, it is water. So first what we are having is, we are having a water or a antifreeze solution. In the collector circuit, this is the circuit where we have water or antifreeze solution that will, that temperature will raise. And we have a heat exchanger named as collector heat exchanger that will take the heat from the collector and it will store in the tank. Then we have another pump to take the heat to exchange with the air, warm air, sorry, the cold air coming from the room. So that is called load heat exchanger. So from here it will give the heat. So meanwhile, parallelly, it will give the heat to the drinking water or other supplies, other domestic water supplies. So why we are using antifreeze solution? Sorry, why we are using this heat exchanger, this separate heat exchanger? Why can't we use the without the heat exchanger? The reason is, if we are using antifreeze solution, that we cannot directly use. So we want to have water in our end use. We can't take bath or drink antifreeze solutions. So we have a heat exchanger, and that helps in water may boil over elevated temperature. So antifreeze solutions has a higher boiling point and low freezing point. So in both ways, this antifreeze solution helps in the system. Okay, so it has the opposite of that. The opposite of that, whatever disadvantages we have seen in the solar air water system, so we have seen here as advantages. Reach easy adaptation we can do, but there are other three problems: freezing problem, boiling problem, corrosion problems are there. But these two can be easily addressed by what I have told as antifreeze solutions. Okay, so corrosion problems also can be sorted out by using a coating on the materials. So that is also can be possible. So overall, solar hot water system has much advantages or much preferable over the solar air water system. So solar hot air system. So that is why we can see anywhere we have solar hot water system installed in our places. Okay, so before getting into the next heat pumps, so what are all the modes of operation? So if at all solar energy is available and there is no need of heat, sunlight is available and I don't want any heat in the building. So which means that the heat will be stored to the storage system. If solar energy is available and it is needed, so directly it will satisfy the building need. Solar energy is not available, heat is needed, the storage has some amount of energy in it. So in that case, the stored energy should be utilized to supply the building need. The fourth scenario is solar energy is not available, heat is required in the building, means the case is night, storage is also depleted, it is also not there. So in this case alone, we have to depend on the other resources like auxiliary energy. So in other cases, in first three cases, most of the time, say for example, about 20 hours per day, we don't rely on auxiliary energy. We can rely only on the solar and storage. But the remaining 4 hours or 3 hours, we may have to use this auxiliary energy. So this is one thing about solar. And the second one is heat pump. Okay, so it is very famous technology. The basics, all the participants are well aware of that. But generally, we have two types of heat pumps, that is compression and absorption heat pumps. So that compression works on electricity and absorption works on heat, thermal, low grade energy. And similarly, the heat pumps are named as source and sink heat pump, categorized as. Like source can be any hot reservoir, that can be air, water reservoir, or ground source, or exhaust air. So, for example, if you take IC engine, the exhaust air is being used for a heat pump. So, some works has been published. And hybrid, so it can be mix of any two sources. And a sink can be air or water. So by that way, we can have a multiple group of heat pumps like air heat pump, water air heat pump, like that. So let me explain a working of a simple air to air heat pump in this slide. Okay. So you can stop me if you have any doubts, or can take a, if you need any, if you want me to go slow, you can tell me, please. Is my voice is clear? Yes.
Yes, sir. Yes, sir.
Yes.
Your
Okay.
voice is clear, and you are doing very well, sir. We are understanding the things, and you are going at appropriate speed.
Okay, fine. Yeah, thank you. Okay,
You're welcome.
so let me explain this heat pump in a practical way. So we have four major components, that is evaporator, compressor, condenser, and expansion valve. The direction, what it is shown, it is not as per our textbooks. So normally textbooks, the heat pump and refrigerator energy consuming devices, it will be in anti-clockwise. It is in clockwise here. So, but that doesn't make an issue in our understanding. So let's take any point somewhere. I am taking this point, exit of the evaporator. So it is at low pressure, low temperature, and slightly superheated vapor. This is the refrigerant, okay? This is the refrigerant. It's there in this circuit. So low pressure refrigerant, low temperature refrigerant, and it is a slightly superheated vapor is compressed because of this compressor. So definitely the pressure will be heavily raised. Because of that, as it is a vapor, slightly near to ideal gas, so temperature is also raised, and it is a superheated region it will reach. So because of this compressor. Then after we have a condenser which is kept inside. So here we are sending the cold air. So normally we know in we have a blower here, something like blower in both the evaporator and condenser. So difference between a refrigeration system and air conditioning system is just these two extra blowers. So in the refrigerator, small refrigerator, the blower requirement is not needed because the size is very small. But in a big room, so we need a blower to pump or blow the air. The size is big. So we are sending the cold air and it takes the heat from this condenser and we are getting a warm room here. So that make our stay comfortable. Due to this, what is happening, the temperature of the refrigerant is slightly reduced and it becomes a slightly cooler liquid. So it condenses. The refrigerator condenses, so it becomes a liquid. The pressure remains the same, not much difference. Maybe there is a slight drop because we know any heat exchanger, we have a slight drop in the pressure because of the pressure drop across the flow. Then we have it will be passed through a expansion wall. So where there is a huge drop in pressure will happen due to the capillary action. And of course, the temperature will reduce and it will be a liquid vapor mixture. As the pressure is reduced, we all know that the boiling point will also reduce. Because of that, some vapor is being generated here. The boiling point is reduced. Because of that, it slightly started evaporation. But the complete evaporation happens in the evaporator coils. Okay, because it acts as a source. So we all said that source and sink. Here the source is the outer side, evaporator coils. So that is source. So that will give some heat. Because of that, it will become slightly superheated vapor. And the cycle continues. So by this way, we can able to achieve that comfortable temperature inside the home. One one good improvement is that we can able to use both solar energy and heat pump together. That will be much more beneficial, because why it is beneficial, I can say you. So in the solar energy system, I told we have to use say 4 hours or 5 hours of auxiliary system, or some gases, natural gas we have to burn. So if we use these two together, solar energy and heat pump together, the auxiliary energy requirement will be further reduced. So it will be much more cleaner. So there are two options we have. So first option is parallel. Second option is series. So parallel, both will operate separately and will give the heat. Okay. So here it will be in a serial mode. Whenever we want to do some repair on some heat pump, we can have an option to whenever we want to service or remove or switch off the heat pump, we have an option to use only solar, but most of the time it is series. Most of the time it is series. Now comes the question, which is better? So whether parallel is better or series is better? Can anybody say which is better? It can be wrong answer, or anybody say? It's a bit tough question also. So what it can be is series is better. That is a very good answer. So why it is better? Because here we have two different outputs that we are not able to control. That is one thing, but predominantly one reason is the collector efficiency is high at low temperatures, and heat pump efficiency COP is high at high evaporator temperatures. So these two requirements exactly matching in the second case, series case. So because of that, the series configuration is much better. So about one slide about auxiliary systems, we have, these are the available auxiliary systems to us. So we can able to store these two, and we can able to directly get from like piped natural gas, PNG, and electricity we are all of course getting from grid. So these are all directly we can able to get, and these two we can able to store. So depends on our requirement. Like for example, if it is a commercial building, like commercial, a very big building, commercial mall, so we can choose the auxiliary based on utilities. If it is a single house, on-site store will be sufficient for auxiliary systems. So these are all about active systems. And coming to the passive systems, so what actually happening is the collection and storage are integrated into the structure of the system. So in passive system, we don't have any pump or blower blowing the air or pumping the water. Okay, so then how it is happening? The collection and storage part are merged into the structure of the building itself. You can say that the windows and rooms behind them are collectors. So we have seen in the first slide, there was a window, so that takes the heat from the outside, so that can act as a collector. So of course, as I told, it doesn't require any mechanical energy, so no movement of fluids through forced convection. Only it may move through natural convection, temperature gradients because of natural convection or radiation heating. So it is having much more benefit because even we are not running the pump. So it is much environment friendly. So there are three concepts are there: direct gain, indirect gain, and isolated gain systems. Okay. Of passive systems. So direct gain, you can recollect the first slide. So this is what is called direct gain. Sun directly heats the living space. So how? So the windows acts as the collector. So through the windows, we are getting the sunlight, and we are getting the building that acts as a storage. It will store the heat, so it can give the heat later stage also. Okay, this is what is called direct gain system. So we can use the shade or some overhang or some cloth to avoid heat loss in the night. So the night we want to retain the heat, so we can have an insulative cloth near to the window, so we can able to retain the heat. Okay. The second one is indirect gain system. So indirect gain is, first of all, what happened? The sun heats the dense material of the house, like this place. We have a thick wall, so we are heating the thick wall of the building. So that thick wall is called a thermal storage wall or trombe wall. So that wall is getting heated first. Then after that, because of convection effect, so the heat will be given to the inner surroundings, inner environment. So, but this is slightly expensive because huge amount of material being invested. So, but you can see here, there is just a window being the receiver. So the glass is the receiver, and so that is much cheaper when you compare with the thick concrete. Okay. The third option we have is isolated gain systems. So isolated gain systems is, we have seen, it's something like a greenhouse. Okay, we have seen in organic, farming, miniature farming. So where we have a sun space. So this is the house. So we have a mirror or glass house, something like that. So that it takes the heat from the solar sun, and that will be circulated using thermosiphonic effect. Natural convection effect. It can be circulated to the entire building. So these are all the multiple configurations available. Depends on the heat requirement. We can have this configuration. Let's say this one, whenever you need less amount of heat, so you can go for this configuration. When you want a moderate amount of heat, you can go for this configuration. When you want more amount of heat, when it is very cold, so you can go for this configuration. So these are the three types of passive systems where there is no fan being used or pump being used. Just our building is getting heated just because of our walls and the windows and the glass. Okay, and there is one more system, the last system, that is hybrid system. It is also getting much attention. So what actually happens is the collection is purely active and storage is passive. So here actually what happens, the collector, here we have a collector. So there is a fan or blower attached. So that blows the air to the collector. So by that way, we are able to extract the heat from the collector efficiently. So the collector temperature should be low. So we should not make it too high to improve the efficiency. So we are just pumping or blowing the air. So we can effectively utilize the collector. So that is the benefit in this hybrid system. Then second thing is even we can able to pump the liquid also here. And the walls, as I already said, the walls can be, we can able to store the heat in the as a passive mode. Okay, so hybrid system is a very good alternative to the active and passive systems. Now, this what I have talked as of now is solar-based heating. So I have just one slide. I don't want to take much time on this part. So solar cooling is also possible. So we all know that the solar radiation, the intensity somewhere starts like this, and it is high in the afternoon or just near to the noon, before and after the noon. So the intensity is very high. And at the same time, the cooling requirement, cooling demand is also high. So if we see a cooling demand curve, it will come like this. So demand of air conditioning is high in the same period. At the same time, we have solar energy available in plenty. So we can we use the solar energy to make cooling. Okay, one way is we can take the electricity obtained from PV or concentrating solar power, and we run our air conditioning systems. This is much simpler. The second way is we can utilize the heat generated. If we have a flat plate collector or even evacuated tube collector, FPC or ETC, anyone, and we can get a thermal energy hot fluid that can be sent to absorption cooling. So we all know about hopefully about vapor absorption refrigeration system. So through that we can able to get cooling effect when the source is thermal. So this is also called as thermal driven refrigeration systems. Normally we have refrigeration, we have two major cycles, that is VCR and VAR. This is mechanical driven or even electrically driven. This is thermal driven. So the solar heat can be utilized to run this refrigeration system. And the third one is mechanical energy itself, like we have a Rankine cycle cooling. We have a power plant type of setup where the turbine is rotating. The turbine is connected directly to the compressor of the VCR. So instead of generating electricity and producing the electricity, we can directly couple the compressor of the VCR system to the turbine. So by that way, we can able to get a cooling effect. So these are all the several methods available, and of course we have. It is possible to obtain even very low temperature like refrigeration is also possible. Solar air conditioning is nowadays it is very common. Refrigeration is also possible nowadays. So just I have two more slides on the second part, solar energy and heat pump together. So one point we should not miss, that is building loss coefficient, which means that we try to retain the heat or the cold within the home. We should not allow it to lose or get it lost. So normally through windows, doors, floor, roof, walls, these are the different mediums through which the accumulated heat or accumulated chillness may get lost to the outside environment. So this should be much carefully or wisely chosen to avoid heat losses. So yeah, a simple table is given here with index like a U value. U represents, we all know that overall heat transfer coefficient. Here it is, especially we are targeting about losses, so overall loss coefficients. So we can see here the highest value of U is 6. In the case of single glazed no insulation, which means we have a single glazed window and we are running our AC air conditioner and we have a very big window, and so we are trying to create a chill environment, but most of the heat is getting lost, cold is getting lost because heat from outside will be transmitted through our windows easily. The coefficient is high. Because of that, we have to end up in spending huge amount of energy bills, right? So if at all, if we go for double glazed, then it is nearly reduced to half. So there are several configurations are available, and we can choose a wiser one like 0.3 or even say 0.9, because as this U value is getting reduced, the cost is also increased. The initial cost is increased. So we have to make an optimum selection among these available. Say we have about 7 things available in front of us. So we have to choose optimally, wisely. And similarly for the wall also. The wall, of course, in certain regions, we can use a thinner wall. So at that time, we can able to reduce the U value. Okay, fine. And when we have used a material having like plaster, so or insulation board, so the thermal conductivity is low. Because of that, the U value is low. The third one in thermal management of buildings, I want to talk about PCMs. PCMs are a special group of materials. Let me go to this slide. It is an energy storage material. So it takes the heat. Like we all know that if any material takes the heat, according to the sensible heat value, the temperature rises. And after that, once it reaches the melting point or the phase change point, then it will also take the heat, but the temperature will not rise. So that is what is called latent heat. And in this, it will be converting to solid to liquid. And after that also it will take heat and temperature rises sensibly. Okay, so these materials, the important thing is, see, for example, if you take a sodium nitrate for an example, the building, I have to use the low temperature PCM. Just for example, I am telling here, its melting point is say about 306 degrees Celsius, useful in solar thermal power plants. Its latent heat is about 172 kilojoule per kilogram. The specific heat is just 2 kilojoule per kilogram. So we can see that from say around 100 degrees Celsius to 300 degrees Celsius, it may store just 2 kilojoule per kilogram Kelvin. But at a single temperature, 306 degrees Celsius, it can able to absorb 172 kilojoule per kilogram. So that's a huge amount of energy it can be stored. So in building, there are many PCMs like RT25, RT24. These are the PCMs commonly used. RT is the commercial brand name, that is Rubitherm. So we all know that there is one more point I have missed, that is organic PCMs. Organic PCMs are like have a lower melting temperature that can be used effectively in buildings. Okay. So coming back here, so I have taken two cases. One is a domestic building. Domestic building, the requirement is low. So just just we can impregnate PCM into the concrete. So by that way, the heat can be absorbed by the PCM and we can able to maintain a comfortable temperature inside. Okay. In the night, when the temperature is reduced, it can emit either in both directions. So we can get this slightly better comfort in the night also. But in the case of commercial buildings, assume we have a requirement for, say, let's say the example like industrial buildings where we need hot air for certain applications. So there, how we can use this is we have the building and we can have a glass plate or cover. So we can send the cold air and we can able to take maximum amount of heat using this air. So we can able to get the hot air that can be used for applications. So this arrow is for like that, and this hot air that can be used for our residential, that is within for the building, residential purpose or some other purpose. Okay. So then by that way we can able to have a comfortable environment within the building. Okay. So the PCMs can be used in multiple configurations. So one such thing I have shown you is capsule. So this is how the capsule looks like. Because PCM can be impregnated in the concrete by two ways, that is microcapsules and macro capsules. Okay, so the microcapsules, the diameter is in the micron level, so we have to encapsulate the PCM in a very small capsules, and it is covered by normally polymers. So macro capsules, we can able to fill the PCM like this. Normally, whenever we do fill the containers, we have to fill with the liquid state PCM. Okay, liquid state PCM we have to fill so that it will reach all the parts, nook and corner of the container. Once the PCM is filled and it will become solidified, while solidification, there will be a small contraction possible, okay, like 5 to 10%, the volume will be reduced. So that is no problem. That is why we are filling in with liquid. That will give some air gap, but indirectly it helps in thermal insulation in the case of buildings. Okay, so normally the thermal conductivity of PCM is in the range of, say, maximum PCMs in the range of 0.5 watt per meter Kelvin. Even lesser values are possible. So these capsules can be directly kept inside the concrete structure. So by that way, we can able to store the heat. So this, the left-hand side figure, these capsules are useful in solar thermal applications where we want to have a we want to maintain the temperature at a very high temperature for a long period of time in a tank, water tank. This is possible. This can be used. And the two other possibility is like a heat exchanger based. This one, it is not a heat exchanger based. The third one, it is directly in contact. It is more of a passive type. More of a passive type where no fluid is given to extract the heat. So here actually even the packed bed or the shell and tube configuration, we can able to store the PCM. So in this case, for example, this is one of my paper where we have modeled the shell and tube heat exchanger based PCM with all the, we have also optimized for about 10 megajoule heat storage. So here the PCM is in the shell side, and inside we have the oil, the thermic oil being passed through it. And here we can have a packed bed. Packed bed normally, generally used for air-based HTF, where we have a turbulent flow available in the packed bed. So the hot air will give the heat to the PCMs packed in spherical capsules, and it will go the cooler temperature, and later it can be utilized. So, and one more thing is the whatever we have discussed now, like this type of PCM capsules, can be installed during the initial phase of the construction only. Because if already there is a house and the entire house I want to install PCM, so that is a bit tough job because we have to make multiple structural changes. So if we have a plan, if you are building a house now, then at the initial itself, if we have a plan, we can choose this macro capsule option. This is the easiest one. But if already built, so in that case, how to do? So in that case, recently one company as Enerseal has come up with a paints in that the microcapsule PCMs are suspended. So the best way in thermal management of any home, as per my opinion, is we have the top roof. Top roof, we can have reflective paints. Okay, high reflecting paints. So it will be white color. It will be white color. So the entire roof is painted in white color, reflective paints. So what happens? Only 1/4 of the heat will enter the house, enter the building. Remaining 3/4, or even in some cases 4/5, will be sent back to the atmosphere. This is a very easy technique in the existing house. If we just have a white reflective paints, it is available commercially in all our brands available in our country. So by that way, we can able to see a nice 4 degrees Celsius decrement in the room temperature. So this is one thing. And the side walls, the recommended thing is PCM suspended paints, because PCM suspended paints can come in several colors. No problem. So we can have our own choice of color, and we can paint the side walls using PCM paints. So this is the best way to manage the temperature or save energy for an existing building. So that's all about thermal management in building. So about thermal management of processor, I have just one slide. I just want to brief you what are all the multiple options available in front of us. So we have again active cooling and passive cooling. So most of the cases where the data centers, we have data centers, huge servers, the one preferred cooling is forced liquid cooling, because the liquid has a high specific heat, high density. Okay, so even better thermal conductivity when compared with the air. So that can take more amount of heat. In only thing is, that can take more amount of heat. Only thing is leakage. Those things should be properly addressed. So what can be done is one heat sink. The heat sink actually is a passive cooling device, but the heat region where we have a heat sink, and there we have a forced convection liquid cooling. This is the best way for high intensity applications, high heat generation applications. The second comes the forced air cooling. So in normal computers, like our own desktops, our own laptops where the heat generation is slightly less, we can use forced air cooling. So we have a fan available, so that will be able to cool the process. And one more option is micro channels. So you have it is similar to a heat sink, but it can be like micro channels. It's so small channels are possible. Okay, so by that way, the surface area is more. So as we go to micro nano level, what actually happens is the volume remains the same, but the surface area is increasing. Because of that, it can able to pull out more amount of heat, the contact area. Then comes the thermoelectric cooling that is based on, it is something like, we can call it as a solid state heat pump. A solid state heat pump. It is something like works on a Peltier effect. So it is very lightweight and very simple and easy to construction and cheaper also. Uh, it is nowadays being used in replacement for VCR systems. The only thing is it doesn't have any moving parts. So that makes it attractive. It is noiseless operation. So whenever a current is passed, so the heat is transferred from the hot region to the cold region. That concept is being used here. So, and the passive cooling where we are not using any electricity or that is pump or blower. So the first one, an attractive option is heat pipes. So heat pipes can be used. So assume this is the heat pipe. So we have a hot region, we have a cold region. So we have a fluid inside, and uh, that fluid can change its phase. So we all know that the heat transfer coefficient for boiling and condensation is in the range of 30 to 50,000 watt per meter square Kelvin. So what happens? Huge amount of heat can be taken from this hot surface to the cold surface. Here it will be evaporated, and here it will be condensed, and the fluid will be circulated. And here, based on buoyancy effect, the fluid will be moving. But in the heat pipe, it is like one direction. So vapor chamber, it is, we can say, a 2D heat pipe. Because normally in processors, it is like something like a 2D surface. So the entire 2D, it's like something like a square processors base. Okay, so entire 2D, we need to remove the heat. So instead of having multiple heat pipes, we can have a vapor chamber where it acts like a thermal spreader. So another name is thermal spreader. Okay, it spreads the heat. So, and it works on the same principle as heat pipe. And the heat sink is very common to us. We all know, we have seen multiple times in the desktops. It's normally we have something like this. We have multiple pin fins attached to a common base. So by that, it will be able to, based on, in simple terms, it based on fins concept. The surface area is high, so it will be able to release the heat. But heat sinks are predominantly used in other systems also, like active cooling systems. And the last one is phase change material. I have already told. So even phase change material can also take the heat from the heat sinks or any processes. We should have an intermediate plate, and the PCM can also take the heat. So that's all the end of first session. So before getting into the hands-on, just I want to have some questions if you have. If there is no questions, then we can move to our hands-on also.
Excuse me. Participants are requested to ask question if you have any question. But the sir has explained it in a very good manner. I think that may not be have a question, any question.
Nice to hear from you, sir.
No,
So I
really,
think
it's good.
Hello.
yes, sir. Yeah.
This is Digvijay.
Yes, Digvijay, sir. How are you?
Sir, very good, sir. Actually, my master's topic was related to this underground heat exchanger, earth air heat exchangers.
Okay, nice.
I'm very much familiar with this passive cooling technique. So very good to see this interaction today. So any
Nice,
model
nice.
you have done in COMSOL related to this?
Yes, we have done many models. Actually, I am using COMSOL right from 2012. So
Okay.
2012, I started my PhD. So initially I developed models on sensible heat storage. That is a passive cooling, passive storage.
So can you share, sir, any model now with us?
Yeah, I can. Means this computer is a different one. I can share it later also. I can share some screens. Yeah.
Okay.
Yeah. Sure. And even my students, my MTech students, one student is working on processor thermal management, one student is working on building thermal management, and 3 students are working on battery thermal management. So actually ours is a research institute. We have more MTech students. So I have in this year I have 10 MTech students. So nearly 6 are working on thermal management.
Okay, so any research work can you share which is done in COMSOL? Any
Yeah,
your
sure.
paper?
Definitely I can share. See, yes. So this is my first paper of my PhD. It's very nicely written, and is all the things are much. The entire modeling is explained very detailed way, and it is published in ECM. It's a very good journal for us. So the modeling part I have explained step by step. All the equations, everything is the what method we have chosen, because in PCMs the melting is happening, phase change is happening, so that is slightly tougher when compared with our normal forced convection cooling or like that. Okay, so I can share. So this model we have developed. So let me share my screen. Like this, there are a lot of I hope you can see that there are many models of COMSOL validation file and heatsink file. So this is one of my MTech student work. We are about to publish within 2-3 days. So it's a heatsink. Okay, we have certain novelties I cannot say now here. So we have successfully modeled, and we can able to show the temperature thing, temperature contour, isothermal contour. It's not the final model, because our thing is that as we are using water as a fluid, we should not reach 100, because above 100 the boiling starts. So that is the critical thing. Whenever we manage temperatures, whenever we publish or do some models, we have to be very careful, because numerical models are such that we have to teach everything. We have to choose the proper physics. Like boiling is happening, I have to choose a proper physics. Then only it will be, the model will take into account. Otherwise, it won't take. So in that case, I had to, when I got result, I should we should apply our knowledge that it should not go beyond 100. So we can see papers in water, the temperature is reaching 120, and the no boiling physics is being incorporated. So that is slightly not perfect. Yeah. So this is one of our recent research work, and battery thermal simulation also we have done. many are there. I just have in other computers. Okay, for time being. Yeah. Okay. This is the existing model in the COMSOL multiphysics. So with we have done some small minor changes so that we just try to find out no other work is being published. So we try to change what change can be made so that previously no work has been done, and accordingly we simulate. Okay. So is there any questions? Can we move to the our hands-on part?
Yes, sir.
Yes. Okay. So the
I
hands-on
request
part.
participants to open their install COMSOL software and follow the instructions from Dr. Hakim, sir. Okay, sir. Participants are asking for 2 minutes break. So
Yeah, sure, definitely. Yeah, I also take the 2 minutes break. Yeah, thank you.
yeah, so we'll meet at 12:20.
Yeah, sure, definitely.
So meanwhile, participants can take break and also open the COMSOL software, which is installed on your system.
Hello, sir.
चालू करा. नाही हो. मॅडम हे तरी वाचतो काय काय बघा. करंट स्टेट्स ऑफ GEE आणि CET. त्यानंतर डॉक्युमेंट फॉर अफॉर्डेबिलिटी ऍडमिशन आणि त्याचं प्लेस ऑफ फ्रॉम वेअर वी कॅन टेक द डॉक्युमेंट्स.
Anush sir, Anush sir, will you mute your?
Open.
Okay, shall we start our session? Yeah. Yes, I think we can start our session now. I'm just sharing the screen. Is it fine? The screen visible? Am I audible?
Yes, sir.
Yes. Okay. Fine. So, okay. before getting into the actual simulations, so I just want to tell the effectiveness of this software. So normally when we do numerical modeling, okay, when we publish a paper, so one important thing is validation. So we have to validate our model with some experimental results. Correct. So there actually that tells us how much our model is solid, that is how much it is perfect. So that validation is very, very important for any model which we develop. So in 1D problems, that is one-dimensional problems, that validation can be done even through analytical way. So the analytical is perfect, that is having no doubt that is perfect. So we can develop a numerical model and we compare with the analytical results. So that will be giving, if both are matching, then our model is correct. So let's take a very simple problem I have taken from the book Sengel. You are aware of that book. Hopefully many are. Hidden mass transfer. Hidden mass transfer from Sengel. I have taken a very basic example problem. Slowly we can proceed. So in this problem, what it is given, a 3-meter high wall. Okay, it is there. The 3-meter high wall and 5-meter wide wall, and thickness is 0.3. Thermal conductivity is given. Temperature of the inner and outer surfaces are given. Rate of heat loss is asked. Okay, so this is a this is the simplest problem in heat transfer in conduction. Okay, so one more important point in modeling is we should not model our final stage model initially itself. We should go by step. We have so many physics being involved. We have so much complex geometry. We try to do the model of a simple geometry and one physics. We got to run the model without error. Then we add one more physics. Okay, we keep on adding physics and we are able to solve without error. This is the approach in numerical modeling. Then we make the geometry complex and apply all our conditions. So by that way, we can able to approach the problem very easily. Otherwise, if we develop a complete geometry, a complex geometry, and we apply all the physics at the same time, then we may not be able to find out where which reason the error is coming. We cannot be able to track the error. So this way it is better. So this is the answer given in this problem. This is a very simple problem. So we are able to do that. So how can we do in COMSOL? So let me open COMSOL. You can also follow. It's many people might have done by now itself. So in analytical method, we should know these formulas. Like, see, for example, we should know the resistance formula. And after that, we should be able, at least if not, we should know the complete formula. And we can able to calculate the heat loss. So, but in COMSOL, let me So first, actually, it is recommended to use a model wizard. I hope my COMSOL screen is visible. Is it visible? I hope it is visible, right? Yeah, yes. Okay. So now I just click a model. So the problem, what it is being given, is it a 2D problem or a 3D problem or a 1D problem? The geometry looks like a 3D, right? The geometry looks like a 3D geometry, but the problem is just a 1D problem. Why? Because the heat transfer is in this direction, one direction, not in this direction and this direction. There is no heat transfer happens in the other two directions. So only in this direction, the heat transfer is happening. So it's a 1D problem. It's a very simple 1D problem. So, but still, we can able to make this diagram. But I just want to save some time and I'm making just a 2D representation of this problem. So let me choose 2D. Even I can do with 1D, but I'm just choosing 2D. So I'm choosing the heat transfer in solids physics. Just keep on adding and study. And it's a stationary problem. Okay, it is not the time dependent problem. So I choose stationary physics, stationary study, and I click done. So it is given here, this side I am focusing on, it is just like 3 by 0.3. So we can easily draw a geometry rectangle. The height is say 3 meter and it is 0.3 meter. So this is the view from this side. This is what I have made. Okay, so now our geometry is done. Now we have to assign the material. So the COMSOL is asking material. So which material I can give? So here there is no mention about material. Here only thing is mentioned with respect to material is K. K value is needed for this material. So K value is given as 0.9 watt per meter Kelvin. Okay, so let me add my own material, a blank material. Okay, I have chosen. So by default, in the solids physics, in the heat transfer in solids physics, we need to use 3 mandatory properties. But you can see from the question, only one is given, that is 0.9. The other 2 are not given. So what is your comment on that? Why the 2 properties are not given, whether it is not needed, or why COMSOL is asking, whether it is asking extra? So anybody can comment on this? So you can see here, there are 3 things are mandatory. The thing is that the COMSOL material and the entire physics is prepared for even all studies, time dependent study also, it is prepared for. So I can tell you one thing, in the physics module, the physics, there is a value, there is a domain level entity that is called initial values. Okay, so there is no initial value needed in the case of stationary problem. So even if you cross check the problem here, nowhere the initial temperature is given. T initial is missing, not given. So T initial is not at all required in the case of a stationary problem. But still, the COMSOL, there is an option initial values. Why? Means that the physics structure is prepared for all type of studies. So in stationary study, you can ignore this. For time dependent study, you have to give this. So that is the difference. Similarly, for material also, we have 3 properties it is asking, but only one is sufficient. So I am giving a random value of 2000 for density and heat capacity. See, you can try one way, like after successfully running the problem, you change the density to 2000 to 4000 and heat capacity to 2000 to 10,000. There is no change is going to happen in the result of the simulation for this corresponding problem. And same way, initial value, you keep anything 1000 degrees Celsius or anything, it will not be going to affect here. Okay, now our material is also done. We have chosen the physics. What is the next step? Next step is applying the boundary conditions. So the left boundary wall, that is 16 degree, and the right boundary wall, that is 12 degree. So I'm just adding a temperature boundary condition. Temperature boundary condition is the easiest one. So left one, I'm choosing 60 degrees Celsius, 16 DEG C, capital C will give you 60 degrees Celsius. Similarly, I am duplicating I'm removing this and adding the second right wall. The temperature is 2 degrees Celsius. So I have defined the problem, that's all. My problem is well defined and I'm just meshing. Let us try with this normal mesh. Very few elements are there, only 62. Still we try with the compute option. We have done the machine and it's a stationary study, so we have just computed and it is solved. Now, what can be found out? Our requirement is, what is the requirement? That is heat transfer rate. Heat transfer rate is what, how? Let's see from the, let's create another 2D plot group. So where we add a surface. So here the default is T. Why it is coming T default? Because in the physics, the dependent variable, the default dependent variable is T. I hope you all can see this, right? So the physics, the default dependent variable is T. That is why in any result node, you add any group, 3D plot group, 2D plot group, the default thing is temperature. Now I am deleting this temperature and I am going to add from the physics, I have a flux called total heat flux magnitude. So this I am adding and I'm just plotting. So we are able to see that 42 watt per meter square is happening, is the heat flux magnitude. Okay, so now I have to go back to the problem. Actually, I want the heat transfer rate in watt. So the area representing here is which area? This area, this A is this area. That area. That area is nothing but 5 into 3 is 15 meters square. So if we just implement, I'm just multiplying. In the expression, I have added a heat flux magnitude and I am multiplying by 15 square bracket m power 2 square bracket closed. Now if I give a tab, the unit is changed automatically to watt. And now if I plot, what value I am getting? Are you able to see the value? Anybody? I am getting a value of 630. So that is the, yeah. So that is the answer here. So we have solved, we have validated our model. So the meshing, you can see the meshing also is so poor. So we have very poor meshing. Still, we are getting the accurate answer. So we have validated our simplest model with a problem taken from example problem taken from Sanjit. So I am saving it as in a folder. I just save it as one. Okay, so this is done. So what? Any doubt in this first question? It's a very simple problem. Any doubt is there? I assume no doubts. So okay, we can go to the second problem. This is a slightly complicated problem. So what I do now is I just try to reuse the, I have already saved this model. So I just save as 2 also, so that I can reuse this model to save. So consider this much height. Okay, height is given with this given. So first I can make the change 0.8 height and 1.5 mm. Sorry. Okay. So this 0.8 is this height and wide is this. We say 1.5 meter. The thickness of 8 mm. Okay, 8 mm thickness. Thermal conductivity is given. Fine. So steady rate of heat transfer, and so inner and outer temperatures are given. So the previous problem is a pure conduction problem. So this problem is a pure convection based problem. That is the only major difference. So heat transfer convection coefficients are given on the inner and outer sides. And it is also mentioned that the effect of radiation is already incorporated in the H2 and H1. Okay, so this one is a glass window. The first one is a concrete wall. So this one is a glass window. So glass windows are very, very important because heat losses happens predominantly in these glass windows. So you can see here there is a lengthy steps. Okay, you have to remember all the formulas. You have a lengthy steps here. So let's see how we can go ahead here. Let me change the 0.8 meter. Okay, rectangle, the height is 0.8 and the width is 8 mm, so 008. Okay, so I have, this is the glass. And the material, we know that the thermal conductivity is 0.78. The remaining two things I don't want, so I leave it like that only. So it's a solid, initial values I don't want. Now the boundary condition is slightly different. It is not a temperature boundary condition, it is a convection boundary condition. So I delete these temperature boundary conditions. So you can see here in this, there is a boundary condition, heat flux. So here there is a option called, there are three options. There is one option called convective heat flux. So here we can able to give the external temperature and the heat transfer coefficient. So both in convective boundary condition, we have to give both. Let me go back to this problem. The room is maintained at 20. So the room means inner side is maintained as 20, but the temperature of water is okay. Inner side is H1. So 20 degrees Celsius, 10 watt per meter square. These two will be in the left hand side, some sides. And this 40 degree and minus 10 is in the outside. So I can give accordingly. So 20 degree and 10. So I can directly write here 20 degrees Celsius and the heat coefficient 10. And I have to choose the left side one. Yeah. The thermal insulation one, we don't want to do anything. Automatically, it will choose on its own based on our boundary conditions. Whatever boundary we have not given any conditions, so those boundaries will be automatically given insulation boundary condition. So I'm choosing the heat flux again. This is again a convective heat flux on the outer side. I click the outer one. So external temperature is minus 10 degrees Celsius. And outside the velocity of air is high. So 40 degrees Celsius. Okay, so I'm just saving the model and I just redo the mesh. Right, we have mesh is done and I'm just compute the solutions. So it will take roughly 2-3 seconds. Okay, it's done. Now, first step is what actually the question asked is. So here, so the heat loss, the steady rate of heat transfer being asked, that is 266 watt. So let me go back to our, I just renamed this to heat transfer rate. Okay, so I just want to remove that whatever I have given for the other one. So here the heat transfer rate is means per watt per meter square is 221.8. So let me calculate the area of this window. We can even incorporate in COMSOL already. So 0.8 into 1.5. So it's about 1.2 meters square. That we have to multiply. And we can see here that into 1.2 meter power 2. It's in watt now. You can see exactly 266.16 is the answer. So I just worried there is a small change in value, whether it is due to accuracy or something like that. But the problem is not with our simulation. Problem is here. Here the values are truncated. It will go like that, and here it will go like 555. As we have truncated, there is a slight error in this calculation, and if we calculate it properly, and it will come with a slightly lower resistance, sorry, slightly higher resistance. So based on that, this value will become 0.6. So whatever we have calculated, so whatever we have simulated, that value is perfectly matching with our analytical solution. Then second thing is inner surface temperature of the window. So one more question is asked: what is the temperature we will feel in the surface within this building, inner surface temperature? So that is approximately minus 2.2. We can able to do a surface average, the derived values column. So let me know if you want to do a slow, or you can let me know. So derived values, there is an average, line average, because the window is in the inner side. So I just want to do a line average. So I click line average, and window is in the inner side I want to do. So I just click the inner side thing, and I am writing in degrees Celsius. If I click evaluate, I am getting a value of minus 2.18. So minus 2. I am getting a value of minus 2.18 degrees Celsius. So our value is actually more accurate, because if you use 266.16 here, it will become 2.18. So we have in both the problems, the first problem is the heat loss through a wall. The second problem is heat loss through a window. Okay, both we have seen. Any doubts as of now? No doubts? So, okay, so we can move to the next problem. It is a heat loss through double pane window. So as I have already told, like in the single pane window, the U value was 6. Okay, it was for a standard size. Okay, the value 6 is applicable for a standard size of some area. So in that case, and also it's for a particular 1 degree, because you value the watt per meter square Kelvin. So, but for the double pane window, it was slightly lesser. So that we can able to check with this problem. So this problem, the third problem is the window size is same, the window size, but we have two such windows we are going to use, and the thickness of the windows are reduced by half. Like previous problem, we have a 8 millimeter window. Now we have a 4 millimeter window, but we have two. In between, we have a air space, that is K value is given, and 10 mm wide. So let's see how introducing this air space between the two panes of the window reduces the heat transfer. So let me save this and let me save as a file 3. So here, if I add the geometry, I want to change it to 4, correct? And I just duplicate, and here the thickness is 10 mm. Okay, then again I duplicate. So here the thickness is 4 mm. Yeah, my things are fine. Only thing is now I have only one material, so it will be choosing all the materials. So I just want to add air material here. So instead of, I can have the option of browse materials, and recently whether I have used or not. Yeah, recently I have used air. Otherwise, you can choose the built-in air. I can add to component, and then. But one thing is very important. So let me zoom it. I hope I have made any mistake. Like, yeah. See, I have made a mistake. Like this corner is same 0, 0 here, but once it moves to the next one, so the corner should be like 0.004. Now I have a, this is applicable, and then next here the corner should be, we should just add and keep on adding the thickness of the previous item, so that we can able to, yeah, now it looks fine. Now there is a, it looks like a double pane window. You can see that here is a one pane, and this is the air column, and this is the another pane. So now let me build for the material. I'm just removing the air space. So only first and last is the glass, and for air we have the inside middle one. But one thing you should be careful, in thermal conductivity they have used the K of T. K of T, how it looks, we are not sure. So it is varying with temperature. Okay, so if you are able to plot, it is changing. Okay, the K value is increasing. It's not a constant one. Right. So it is recommended. It is better. I just want to change the K value to the value given in the question. Let me check the value given in the question, 0.026. So I just move to 0.02. 0.026. I have changed the thermal conductivity value of air. Now everything is done. So heat flux, I hope I have to retain the same thing. Yeah, same problem. Everything is remaining same. So just we have to confirm the things, like heat flux 1 is correct, chosen properly. Temperature is given. Heat flux 2, this also chosen properly. Yeah. Then I can do a mesh. It is saved before running, and just I compute. So it also takes just 3 seconds. So we have computed the value. So now if we go to heat transfer rate, okay, again the area I have to properly check. The value is Q equal to 69.2. So exactly the value is matching. The value is 69.25. Yeah. So now we can able to see that we are able to match exactly 69.2. Actually, it will be 69.25 is the correct value we are able to match. And okay, one inference we can able to note that the previous problem for solution 2, the value, the same value is 266 watt. So heat loss was more but here it is the heat loss is less. And even one good thing is that if you want to find the temperature of certain surfaces, we can easily find out with the line average formula, line average method. So inner surface temperature of the window. So if you click line average and it's already chosen, if I just do evaluate, we can see that we are getting a temperature of 14.229. That is a much comfortable temperature to stay. So even in the problem also, it is coming 14.2. Correct? So these three problems are very, very basic problems, but we have cross-verified with our analytical. So, but in the real time, yeah, yes, please, you can ask a query. Yeah,
Good afternoon, sir.
definitely. Yeah, yes,
Actually, while you are selecting material air,
yeah.
you have changed the thermal conductivity
Mhm.
from some temperature dependent parameter to the constant one.
Yeah, yes.
By default, it is a temperature dependent. So if I am selecting a temperature dependent parameter and on that piecewise equation, can I write my own equation?
Yes, yes, of
It
course,
will
definitely.
validate.
Definitely it is possible. So main advantage of COMSOL is you can have your own material and you can write out your own equations for all the things. And it is not only piecewise, you have multiple options. Interpolation is also there. Okay, interpolation is also, because sometimes what we used to have, we have at different temperatures like 20, 30, 40, you have values of specific heat or anything, thermal conductivity. So you can do a interpolation function is also possible.
Okay, we can do both interpolation as well as piecewise
Yes,
if we have the equation.
everything is possible, but only one we have to mention the name, because see here you can see from the bracket CP eta, so we cannot have the duplicate thing. Interpolation K. Yeah. So no function name now, label also K. Okay, I think if he's while doing a simulation, it will throw error. So only thing we have to keep a unique K. Yeah. Yes. Okay, right?
Yes, sir. Thank you, sir.
Thank you. So why I have changed here in this case, the reason is because we want to do with this problem. What it is, I have taken as a sample problem. There it was given 0.026. Is given 0.026. For that purpose, I have chosen that value.
Yes, sir. I got it. That
Yeah.
one.
Even any material property that may have a behavior like a sinusoidal behavior, like there is an increase at one point and after that there is a decrease. So you can also use analytic function. Analytic function is one good option rather than piecewise. So yeah, analytic functions. In piecewise, what is happening? The piecewise, what is happening here? So you have two ranges or three ranges where you have three different functions. So that is why you can see here in piecewise somewhere here. Here it is very simple. But here they have used piecewise, but they can even use it for. If piecewise is much better if there is much highly nonlinear and you have multiple pieces and you have a function for each piece. So 200 to 400 you have a separate function and 400 to 600 you have another function. In that case, piecewise is much better. If you have only one equation for the full range, then I recommend analytic. So analytic is the easiest way. Okay. Yes. So okay. So now we have done this 3 problems. Let me take one more problem in building and we move to processors. Okay, this 4th problem is a bit complex problem, a bit tougher one. So what I do is, we have a lack of time. I have already done this problem. I directly open this so that it will save some time of us. So yeah. So first 3 problems I have saved, and here the 4th problem, the geometry is very, very important. Like, see, for example, first we'll understand the problem. So what it is being told here, a 3-meter high and 5-meter wide wall. So 3-meter high, okay, and 5-meter wide wall, long cross-section bricks. So this is the bricks dimension, and as you know, in the wall you have multiple bricks, right? So the brick values, HK value is given, separated by 3 centimeter thick plaster. So you have a thick plaster in between the bricks. Okay, but there are also 2 centimeter thick plaster on each side of the brick. Okay, so here there is a 2 centimeter thick plaster on each side of the brick. This is a 2 centimeter thick.
Sir,
Yeah.
can you mute this Hitesh Kumar Gupta?
Okay, 1 minute. I think it's already muted. Yeah, it's fine right now. Yeah. So now, yeah. So, and we have another 3 mm foam. All right. So first, let's focus on the geometry. So what I am focus on one more thing. So how many bricks I may have? That is a question. So we can see here a brick, and together with its plaster and the height, it takes about 25 centimeter. So 25 centimeter is the height wise. So here we have a 3-meter high wall. So which tells that it's like 300 centimeter. So divided by 25, you will get a 12. 12 bricks are in the top, 1 by 1 in the above. Okay. So that we are going to do. So now let me draw from the left hand side. So left hand side we have a foam of 3 millimeter. So that is what here the first thing is 3 centimeter of 3-meter height foam I have built. Then what is happening? On both sides we have 1.5. So the bottommost plaster will be of 1.5 centimeter, and we have a brick, and here we have a 3 centimeter. Okay, so for that purpose, the bottommost plaster I have kept as, okay, so let me draw the left hand side. Okay, left hand side I have 2 centimeter for foam that I have added. Then next another plaster, this one, okay, I have done the complete vertical. 3 are there, 1 plaster foam and 2 plaster I have done. Now in the horizontal, I have added a 1.5 centimeter height plaster. So now next I'm going to add the brick. Brick dimensions are given as accordingly I have added. So one thing we have to be careful whenever we add a brick, the position we should be properly changing accordingly. So next I am adding a plaster horizontal, is thick one. Then I am doing an array. I hope you are aware of array. So array is nothing but just repeating how many plasters I want. So I have 12 bricks. So between I have 11 plasters. So I have 11. So similarly, bricks I have 12. So I have to repeat Yeah, I have 12. Okay, so then at the top, I have to have a small plaster. I have just added now. Now the geometry is done. The materials I already added concrete, brick, foam. So concrete I have chosen the default one, but the thermal conductivity value was something different. But I have given the thermal conductivity value of the problem itself. Okay. Then going to the physics, we have heat flux on the one side, that is 10 watt per meter square and 20 degrees Celsius, and the heat flux on the other side 25 and minus 10 degrees Celsius. So this was given in the problem, and we do just a mesh, and if we run, okay, so see, this is such a complex problem, it just took 4 seconds. So if we try to solve by pen and paper, so we have to find out the resistance each, everything. Then we have to add all the resistance properly, because here the parallel concept is also there, serial concept is also there. Then total resistance, then finally we can able to find out the Q dot value. So here finally we have directly, we can go to HTR, and I know the area should be, area is also I have given as default 15 meter square, because in the problem it is given 3 meter and 5 meter. So 15 meter square I have already given. So what is the answer for us? HTR? HTR is changing. HTR is changing because it is because there are different components being there. That is why the HTR being changing. Okay, so but heat flux will be the same. So I'll just remove the area and plot. So the average heat flux, okay, we can do it in better surface average. Okay, the surface average will do, because entire surface I have chosen, and I just click evaluate. We can able to get a value of 17.455. So 17.45 is almost equal to 17.5. This is the answer we got. And the same way 263 is the total heat flux. We can easily able to get by multiplying with the 15. So by the way, this problem also we have done. So here one confusing thing is there. That is,
Sir,
yeah.
I have one question. In COMSOL, how to calculate that total heat rate, 263 watts?
Yeah, correct. So 263 watts, how we are calculating Q equal to that flux into area. So area, let me tell you here, in the parameters, I have directly given the area, because in the model, I have not considered the wide, means I have just taken this part. This part I have not taken.
Without using area, like directly can we calculate Q?
Directly we can calculate. In that case, we have to model full 3-dimension, because this is the area of our focus, right? So in that case, we have to have a 3D model.
Right, okay.
Right. So as we are not having that area, so we are manually incorporating the area, right? So that's all. So if you just multiply here with area, and the what will come and evaluate. So 261 it is coming. So 17 is the flux and 261. So both are almost exactly matching. There is calculation truncation error in this problem, not in our COMSOL model. Okay. So these 4 problems are relevant to buildings. So one thing I want to show for processors case, just one simulation I can tell. So this is the heat sink model which I have developed. So in COMSOL, there is a option of creating critical geometries in a very easy fashion. So if I start from scratch, it will be much better. But one problem is time. So what I have done is, okay, let me start from scratch. It will not take much time. So let's choose Model Wizard 3D, and we use one physics called conjugate heat transfer. Conjugate heat transfer. What is conjugate heat transfer? Conjugate heat transfer is nothing but the conjugate heat transfer is nothing but heat transfer plus fluid flow. So during the fluid flow, the fluid is exchanging heat with the surroundings. That is what is called conjugate heat transfer. So we have chosen the appropriate physics, that is conjugate heat transfer. Of course, the flow is laminar in our case because in processors, if we have a turbulent flow, then it is mechanical damage also may be an issue. I just go to study. It's a stationary problem, so I just click done. So how we have to create a heat sink? It's very easy. You can just follow me, like right click. There is a option here like parts. There is an option, please make a note. If you right click geometry, there is an option parts. And there is an option parts library, part libraries. So if you click this, there are some default parts are available in geometry, which are a bit tough to make. Okay, which are a bit tough to make. See, this part are slightly tougher to make on our own. So those things are already made by COMSOL inbuilt, and we have to just give the radius or those type of things. So similarly, in the heat transfer models, there is a nice heat sinks library. So there are dissimilar border, parameterized pins, heat fins. Okay, so let me choose any one of these. Let's talk straight fins. So I can just add to geometry. So if I click build, immediately my heat sink is ready. Okay, so only thing is we have to, we have to just change the values of this. It is very easy to understand also. So this is the 38 mm is the fin height from the Z axis. Similarly, Z base, the small base is there, that is 4 mm. Y base. So in Y axis and X axis, it is say 50 mm. 1 minute. So this is very easy to understand, even chamfer. Okay, one thing I would like to tell, like there are some parameters that is defaultly set to 0. What does that mean? So if it is 0, that is disabled. If it is 1, it is enabled. So let me make this notch as 1. And just again build all objects. You can see that there is a L notch. This is the notch, and that notch width also can be changed. So if I change instead of 5, 10. Okay, you can able to see that. Sorry, I have mistakenly deleted that square bracket. Okay, so it should be millimeter. You can see that in the height, the height is increased. Okay, like that, you can able to do a lot of changes. If I make this notch to 0, then the notch will automatically go. Similarly, chamfer, everything you can try. So that and all will be slightly practical. Chamfer, if you give the top, why chamfer is needed? Because in the electronic packaging, we have to properly fit it. It should not be any hanging parts. So it should be properly fit in the chamber. So there may be some projection. So it will be touching to the other component. It will be the assembling should be in that way. So that's why chamfer is needed in some case. So I'm just deleting 0, and you can choose fillet. Number of fins can be improved, increased, for example, 8 fins. So automatically the fin number will increase, and even it will even the offset. So offset in the y-axis. So in the x-axis you can have a 2 mm offset. So you can see that there is a small gap given on both sides. So like this you can able to generate the geometry. Okay. So next thing is how to solve a problem. Okay. Let me have a view. Assume in this x direction air is flowing. I don't want to be in this direction, so I can rotate it by 90 degrees. Yeah. Now it looks fine. So in this direction, air is flowing and it is good. So now I have to add just one block because to define the air. Okay, so what will be the height? Let me check it here. How much is the height here? 50, 50 and 38 or 42. So it should be more than that. So which should be, say, lightly 50 means 70 mm. 70 mm and depth can be also 70 mm, and the height can be, say, 42 means 52 mm. One problem is we don't know which corner X we should keep. So just for time being, we'll just build select. So then we have to adjust the thing. We have to adjust the, because it is in 0, so it's here. So we have to do the minus. So in the x-axis, what is the length? So it will be approximately x base is 50 mm. So here we have to give a corner minus 50. If we do this way, x is now it is perfect. X-axis it is matching, but we need to have a 10 mm offset. So we can keep minus 60. Yeah. So let me choose the wireframe rendering. No, not this. Transparency. Yeah. Next axis is fine. So now the y-axis it has to come in minus. Let's see. No, it is slightly about 20. Yeah, not even 21. Yeah, it is perfect now. Okay, so y-axis is fine. So in z-axis, see, you can see a projection over here. So that much base we have to base is 4 mm. So 4 mm we have to reduce. So position minus 4 mm. Now it is fine. So now why we have done this, because this outer box is the airflow. Air will be there, so we can choose a material, browse material. We have air, and let's see, built-in air aluminum. So both materials we have chosen. So air is nothing but this outer one is air, and aluminum is the rest of the thing is aluminum. We have done. So, but one thing is aluminum is a solid. So in fluid, in the laminar flow physics, we have to keep only the water, the air, fluid. In the heat transfer, everything is there. So it will not create any issue. So let me problems. Okay, so we have now successfully developed the geometry, materials. Solid is perfectly chosen, but fluid is not chosen here. Fluid is the outermost one. Okay, initial values, everything is perfectly chosen. Now we have to just give the boundary conditions. What is the flow boundary condition? We have to give inlet. Inlet is this, and we can give say 0.5 meter per second. Similarly, we have an outlet that is here. We can use zero pressure. So our laminar flow, everything is completely defined. So, but coming to the heat transfer, we have to define the inflow. Inflow is this region. So, what temperature the fluid is coming. Similarly, the outflow is this region. Okay, so we have completely defined our things. Only thing is the boundary. So our processor is somewhere here. This guy is the processor. Here the heat flux will be generated. Heat will be given. So we have to give a boundary heat source. So you have to carefully choose the heat sources. There is a boundary heat source. You can choose this boundary. You can choose say 200 watt per meter square or whatever the heat rate we can give say 200. Now our problem is completely defined. We have to just do a meshing. We just confirm in non-isothermal flow whether we have laminar flow is chosen or not. Meshing, actually, we can even do a coarser or even coarse mesh because it's a stationary problem and the velocity is low and laminar problem, not much high velocity, the mesh can be reduced. And most of the boundary is entire volume. Of course, the air volume is more, still the mesh can be reduced. Yeah, so you can see here that 13 lakh 44,000. So this much mesh is not at all needed. So we can give coarser. One lakh 42,000 it came. So if we just click compute, of course, non-isothermal flow is enabled. We have checked. So it will not take much time. 39% is almost done. So I have told the steps, but post-processing is the very key thing which I haven't told much. I hope that the COMSOL experts have explained some of the post-processing things. So the convergence plot is coming, so it is converging. Yeah. So I think I can show the output. It will successfully run as it is already. It is converging, so it will successfully run. I hope it will take some time. So the net output looks like this. I already have a successfully run model. Or of course, the convergence is faster, so it is quickly able to solve this problem. It will take just less than a minute time. So here you can see, as soon as the convergence is better, the percentage completion is also increasing at a faster rate. In the initial phase of the problem, the percentage like 0 to 35%, the time 0 to 30% of the time, less than that it will take to 35 to 100 because the convergence value is very low. The error value is very low. So, and one more thing, solver part also I haven't touched much, but solvers is a very important thing which needs more fine tuning when it comes to highly nonlinear problems. So there are different solvers available, and that COMSOL by default it chooses the best solver. That is a good thing with COMSOL when compared with other software. So whatever things are there, the mesh, we have physics controlled and we have user controlled is available. And similarly, we have multiple options available in front of us in COMSOL to choose. So as it is a multi-physics problem, both heat transfer and laminar flow is parallelly being solved. It is taking time even in the case of a stationary problem. Okay, so then you can think of how much time it will take for a time-dependent problem in multiphysics. Because here we are only focusing on space discretization. So where in time dependent, the time discretization is also important. So we have just spent around, for the last problem, we spent just maximum 5 minutes, and we are able to successfully run the problem and get the results. So if we dedicate more time to COMSOL, we can able to develop complex problems, very, very complex problems in a short time. So finally we have done. So you can see that the temperature, okay, it's very, very high. So let me show in degrees. So we can able to visualize, or it's 250 degrees. So, and even in color table, and this rainbow light classic is much better because it's able to separate in multiple colors, or even, yeah, this is also a good representation. As the velocity is low, as the velocity is very, very low, the temperature is high. So we can increase the velocity and we can able to see that the temperature can even go down. Okay. So I hope these are all some basic problems. I hope it will be useful to you. I think with this, I can try to conclude my presentation session.
Okay. Thank you, sir, for this wonderful presentation on thermal modeling in COMSOL. So in first theoretical session, you explain very nicely the passive cooling techniques, and in hands-on, you explain the solid conduction problem in COMSOL. So in that, I think that problem, the heat value was very high. That 200 watts is high. That is why temperature was coming very much, because yesterday only I had solved that problem. So I had given 1 watt power, and I was getting temperature around 200, 100, etc.
Okay.
So yes, so that depends on the input value also, I think. So again, participants, if you have any questions, you can ask. Already sir has given his contact details. So those who are planning to undertake any projects related to the domain related to Hakim sir, they can contact sir.
Yeah, of course, we have a PhD admission. I have vacancy this summer for PhD scholars. Yeah, if anybody interested, you can contact me.
Yes. So I guess that's it. Participants are, I guess, very happy with the presentation. I wish you all the best for future research project and endeavors, Hakim sir. So with this, we'll stop here. Thank you very much, sir. Thank you for your time, and thank you for your guidance.
Yeah, thank you, Digvijayji, for allowing me to present here. Yeah, thank you.
It's our pleasure. Thank you. So I think you are the host, so you can
okay. I have
stop the recording. First, stop the recording, and then you can end the meeting.
Okay.
Yes, I am there, sir. I will stop the recording. No problem.
Yeah, I will change the host. Yeah. Oh, yeah, sorry, is the host. Yeah.
I will stop. No problem.
Thank you.
Thank you.